So here's problem 23 on chapter 13 on page 414. I'll read the problem. It says, three objects of equal mass are located at three corners of a square of edge of length L as shown in the figure. Find the gravitational field at the fourth corner due to these objects. So here we have three identical masses. Here's the origin right here. And we want to know what is the gravitational field at this origin. And so let's solve this. Well, first of all, I think you can see that, look, if I put a little test mass right here, little m naught, it's going to be attracted to this mass. It's going to be attracted to this mass. And it's going to be attracted to this mass. So what we have to do, so these are the little gravitational fields due to each mass. Now to get the total gravitational field, we need to add these up like they're vectors. So let's do that. I'll call this G1, G2, and then we'll save the hard one. We'll call that G3. And I'll say that G is equal to G1 plus G2 plus G3. Now, the gravitational field is how much force you would get per unit mass that you would put at this location in space. So it's force per unit mass, or force newtons per kilogram. And to figure out what G is, okay, here's the equation for it. Gm over r squared in the negative r hat direction. And negative means it's an attractive force. It pulls you in. It doesn't push you away. It pulls you in. And so we call that pulling you in the negative r hat direction. So this guy's pulling this, this, and then what you do for the direction, you just kind of do it by inspection. Okay, this mass right here is trying to pull this guy in. That's in the j hat direction. So let's take a look at G1. And, well, in terms of what's given, you have G, m, over, and then r squared is just L. So it's going to be L squared. And what direction is it in? Well, it's going to pull you up, and we'll call that the j hat direction. Positive j hat direction. It's pulling you up. It would pull a test mass up. Does that make sense? Okay. Quite often you add the direction by looking at it and saying, oh, what direction is that? Oh, it's in the j hat direction. And then, of course, G2, we'll make this G2 right here, is equal to Gm L squared. It's the same mass and the same distance away. And it's in the I hat direction. So we're going to add these two together. That's pretty easy. But then what about G3? Now G3 is the one that's a little bit more challenging. So let's take a look at it. Well, it's being pulled at a 45-degree angle. And well, let's figure out what the magnitude is. It's Gm, but what is this length right here? If this is L and this is L, this would be root 2 times L. You remember that? Okay, the hypotenuse of a, well, it's L squared plus L squared. Take the square root, you get the root 2 of L. But it's squared, right? So it's this distance squared. So it's root 2 of L quantity squared. And we'll say that's NA. That's this direction right here. So we'll worry about the direction here in a second. Let's go ahead and well, we'll just call it negative r hat just to be complete. But so this is Gm over 2L squared. Okay, but now we're going to break it up into its components. It's here's the magnitude of it, but we want its x component and its y component. And its x component, well, we could say this is 45 degrees, or we could say it's, we would take the cosine, the hypotenuse. This is the magnitude of, here's the hypotenuse. We want the adjacent leg, and so you'd multiply by cosine theta. But what is cosine theta? Cosine theta is the adjacent over the hypotenuse. So that would be, the adjacent is L over the hypotenuse, which is root 2L. Well, it's root 2 over 2, right? So that'll cancel that. And that's going to be in the I hat direction. So in other words, this is cosine theta times the hypotenuse gives me the horizontal component here, plus, and then now we need the vertical component of G3. It's going to be the hypotenuse times the, same thing, right? The opposite over the hypotenuse. Is the sine of the angle. And I'm probably off screen. Yeah. Okay. Well, this is kind of messy. Let's clean this. Let's clean G3 up a little bit. So this L goes away. You have Gm over, and you've got 2L squared, but you have multiplied top and bottom by root 2, and you get root 2 over 2. And the I hat. And then we can clean that up, make that a 4. Let's just do that. This becomes 4, so G3 is equal to root 2 Gm over 4L squared. And the I hat plus the same thing, root 2 Gm over 4L squared in the J hat direction. But to get the overall thing, we have to add all these together. So we have to add G1 plus G2 plus G3 together to get the overall gravitational field at this point. So let's add G1 to this. And notice that G1 is in the J hat direction, so we're going to add it to this. And then, we'll add G2 first. So this is Gm over L squared in the I hat direction, plus this much in the I hat direction. Well, I can write this out a little bit nicer. We'll pull a GML squared out of so GML squared times 1 plus root 2 over 4 in the I hat direction, plus GML squared 1 plus root 2 over 4 in the J hat direction. And I would leave the answer like that. Is that how the book did it? In terms of the answer? They might have combined this. And, this is chapter 13. Number 23. Oh. Yeah, they Oh, for direction, they put towards the opposite. This is correct. You could find the magnitude of this, magnitude and direction, and essentially they did it in polar coordinates, the answer in the book. So let's go ahead and do that. This squared, so it's basically going to be all of this times the square root of 2. So the magnitude of G is equal to the square root of 2 times this. So root 2 GM over L squared times, well, we'll put the root 2 in the, it's too late. 1 plus root 2 over 4. So we're going to multiply this. We'll just multiply this in here. And we'll get GM L squared. And then if I multiply root 2 in here, I get 2 over 4. So I'll get 1/2 and then plus root 2. And I think that's the answer they have in the book. And then that's the magnitude of it. And then for the direction, they said towards the opposite corner. Well, what does that mean? That means, you know, in this direction. It's being pulled in that direction, like that. Okay. I think that's what they said. Is that what they said? For 23. Yeah. Yeah, that's what they got in the book. So, geez, I must have done it right. Okay, so here's the whole thing right here. I'll just put 45 degrees. I like that better. I would have just left it like this. But either way, that is all.